Augmented reality, mathematics through the coordinate plane. Outside the window, we see an ordinary alley, but on the smartphone screen, a giant humpback whale swims above the rooftops. Its smooth skin and even splashes of water seem close enough to touch. We call this scene where virtual images are layered over reality, augmented reality, or AR. How can such a scene come to life inside a man-made device? The secret is a fixed spot. Even if we take one step, the whale on the screen does not drift away but stays right on the roof. AR turns real space into a language of mathematics we can understand. Then AR makes a spot that the virtual image can call here. What we need first, even before colorful graphics, are coordinates that hold that spot exactly. AR mainly builds coordinates in two ways. One way relies on absolute coordinates. Sensors such as GPS, compasses, and gyroscopes tell us where we are right now. Information such as nearby subway stations, gas stations, and directions is layered for us to see. Another way uses relative coordinates. By finding a reference point on the screen, such as a book cover, poster, or company logo, we say, "Let us use this as the origin." In the past, special picture markers were used as signposts, but nowadays, methods that recognize objects themselves, called markerless methods, are used more often. All of these methods usually happen in three steps. First, through tracking, points in the real world and the virtual world are matched to keep the coordinates steady, and then two-dimensional and three-dimensional graphics are created and placed carefully on the screen. If the coordinates wobble, the whale misses the roof and floats into the air. The power of AR is decided not by how real it looks, but by how well it stays in place. The person who showed this idea of a fixed spot most clearly with mathematics was Descartes. It is said that he watched a fly move back and forth while lying on a camp bed and looking at the ceiling. If we only say it went over there, it is vague, but if we draw one horizontal line and one vertical line, it becomes clear at once. When we write the fly's position as a pair of numbers, x, y, space becomes something we can work out with numbers. However, Descartes did not create coordinates simply because he needed a convenient notation. He often wondered why philosophy does not build up as clearly as mathematics. Mathematics sets a clear starting point, and from that starting point, it builds logic step by step as it moves forward. The coordinate plane came from his belief that we should understand the world on an unshakable foundation using mathematics. On the other hand, he was said to be dissatisfied with geometry's dependence on the senses. Even when solving the same figure problem, some people draw helpful lines and solve it, while others lose their way. Algebra was different. If we set up symbols and follow the rules, everyone can walk the same path. So he translated geometry into the language of algebra. If we fix a point as numbers, lines and curves also become equations. A figure becomes an equation, and an equation becomes a figure again. That is why Descartes is honored as the founder of analytic geometry. The coordinate plane opened a wide new path. A figure is no longer just a picture we draw by guesswork, but something we can work with using equations. Equations do not stop on paper, but become tools for understanding space. Today's AR shows us this result in very ordinary scenes. AR works between the two-dimensional screen the camera sees and the three-dimensional space where we stand. It changes and matches the coordinates so the images stay lined up. If we think about it, our daily lives also run on coordinates. When we choose a meeting place, find our way, receive deliveries, or record our workouts, we are always asking, "Where am I?" Whether in technology or in life, if we set one reference point correctly, things that were blurry begin to align. The future where we layer meaning over reality may also begin with deciding that where.